Hello, Yuvraj. Am I audible?
Good afternoon, sir.
Good afternoon. How are you?
All good, sir.
Lovely. So, since you've
So I
joined,
did the assignments. I had some doubts in my assignments.
yes, go ahead. Go ahead.
So, do you have the access to the assignments right
I
now?
do
Like, which?
not. I do not have the assignment with me. Could you tell me the question? You're having problem.
Sir, I'll have to log into. Sir, can I open the assignment meanwhile being in the class on the same website, Learnivio?
I'm sure you can do that.
1 minute. I'll just make another tab and log.
Yes.
Assignments. So one of the question was that 1 second, sir. Then I guess there's some glitch. Okay. 1 minute.
Yeah, no problem. No problem. Hmm. Yes.
Yes,
Yuvraj,
sir. One of the question.
Yuvraj,
Hello.
yes. So could you just turn your video on? That'd be okay.
Yes, sir. 1 minute.
Yes.
So am I visible?
Yes, yes.
Yes. So I got the question. Uh,
Hmm.
it's question number 8. In the given figure, two tiny conducting balls
Hmm.
of identical mass M and
Hmm.
identical charge Q
Hmm.
hang from non-conducting threads of
Hmm.
equal length L.
Hmm.
Assume that theta is so small that
Hmm.
tan theta is
Just theta.
almost equal to sine theta.
Huh.
Then for equilibrium, x is equal to like
Yeah.
how can I say that? I'll just show it by drawing it over.
Think I understood the question. Can you show me the figure if that's okay? Hello, Yuvraj, are you there?
Uh, Sorry, sir, I got disconnected. Wi-Fi was.
Oh, no problem. No problem. Yes.
Yeah. Yes, sir. So this is the figure. If you are able to.
Okay, I am not able to see that figure at all. कैसे करता है?
Because it's basically, yes, sir. Let's make a angle theta and the other ball going in the other direction.
Could you just show it again? Ah, okay. So the half angle is this half angle is theta. Okay, so both of them
Yes, sir.
have mass m's and some charges q on them. Okay,
And we have to find x, which is in between the both of the, yeah,
you have to find
x, which is in between both of the masses.
as in could you repeat the question once again? I'll just
So,
write down the question.
we have to find this part, this x.
Can you repeat the question? Total question, पूरा question एक बार repeat कर दो
Yes, sir.
because
In the given figure, two tiny conducting balls of identical mass m and identical charge q hang
hmm,
from non-conducting threads of
hmm,
equal length L. Assume
hmm,
that theta is so small that tan theta is almost equal to sine theta.
hmm.
Then, for equilibrium, x is equal to.
Oh, for
Like they have
equilibrium
shown
x.
it in
Okay,
diagram.
so you just need to draw the free body diagram. So essentially, let's take this mass. Let's call this one and let's call this two. Let's take the first mass. You have mass m. You have charge q on this. What are the all the forces that are acting on this? There's obviously mg that's acting downwards. There's a tension that's acting at an angle theta with the vertical, right?
Yes,
And there's a charge force, right? Because both are at some distance x. Let's call this the Coulomb force. Now, all one needs to do is just resolve things, right? So let's resolve this. So you have t cos theta up here, and this is t sine theta. So essentially, for equilibrium, what you have? You have t cos theta is equal to mg, and the Coulomb force, which is just t sine theta, which is just k q, so small q squared over over x squared. Okay, how many variables? How many
so but
forces?
if the mass are so if the mass are equal and the charge is also equal,
Hmm.
so wouldn't the equilibrium lie in the center of both the masses?
The equilibrium position. No, see, the equilibrium position will be here only, right? This is the equilibrium position. This is a position in equilibrium. The system is not
Yes.
going to move because what essentially is happening is that the total force
Sir, I
on
was
both
talking
the.
about the equilibrium x.
I'm sorry.
Sir, I was talking about the equilibrium x. Wouldn't the x be in between both the masses,
X
like
X
exact between?
X
Because
X is just
masses
the
are equal.
distance between the two, right? X is just the distance between the two. X just represents the distance
Sir,
between the
I
two.
guess. Okay, sir. Sir, I thought it's some point in between both the masses.
Okay, so think about it again. Um, let's
Can I
let's
share the
assume
screen out?
let's let's assume there isn't any charge on both these balls. Okay, so essentially what will happen,
Yes.
you'll have the first ball and you'll have the second ball, which is just sitting there without any distance between them. Correct? Yes, no, maybe.
Yes, sir. Yes, sir.
Lovely. As soon as you give them some charge, what will happen? They'll start repelling each other, and then they'll go to an equilibrium position, which is some distance x away, correct?
Oh, okay, sir. Got it.
So essentially, what you need to find out is this position, this distance x. How far away do they settle down? These are the two equations you have. How many variables are there? Well, you don't know the
So,
tension.
sir, I have a thought of doing this question. Can
Okay.
I explain?
Yeah,
Yes,
yeah. Please
sir.
go ahead.
So, what we know is that the mass is given as m. Okay, and force is equal to mass into acceleration. So
Hmm.
acceleration will be zero. The force, total force, net force will be zero when both the masses will interact. So
Absolutely.
what that tells us is we have to find a certain distance between these two masses through using the formula. What do you say? T sine theta is equal to k q square upon x square should
Uh,
be equal to zero
T sine theta
because tension will be
minus
zero.
T should be equal to zero. This is what it should be, right?
Yes, sir.
Yeah.
Yes,
So that is essentially T sine theta is equal to KQ square over x square. That's exactly the same thing, right?
sir.
It's just taking the minus sign, the thing here on the other side, correct? So if you just take this on the other side, what essentially you
Yes.
will get is T sine theta is equal to KQ square over x square. But that's only the x component. The y component is also important, right? The y component also you need to equalize, you need to balance. So first balance
Ji, sir.
the x axis and then balance the force along the y axis, and hence you'll have the force balance along all axes. That's essentially how you progress. Now, once you've written down equations, always stop and ask yourself how many variables are there. Here, first variable is the tension. You don't know what the tension is. So this is a variable. Theta, well, it's some angle theta, but it's really, really small. And theta, we know, will be dependent on x, right? Because whatever theta is, this is x over 2. So your not tan theta, what is this? Cos theta, sine theta, yes. Sorry. So your sine theta is just x over 2 over L, correct? From this
Yes, sir.
triangle. And sine theta, I know, is approximately just tan theta. So just keep that
Equal
in
to
mind
tan
that
theta.
that will be useful later on. So what is the other variable? The other variable is obviously x. The rest of the things you already know. So you have two variables and two equations. Very nice. You can solve the system. How do you go ahead and solve the system? Well, how you need to remove one of the variables. Which variable do you want to remove first? Obviously, the tension, because tension is something that you don't want to calculate. So let's
Yes,
remove
sir.
that. How do you remove that? Well, take this as
Subtracting.
equation one, take this as equation two, and let's just divide the two, right?
Yeah, yeah.
So what do you get? You get T sine theta over T cos theta is equal to KQ square over X square over mg over 1, correct?
Yes.
Lovely. So अगर इतना it's
So,
absolutely
sir, we get that tan theta is equal to kq square upon x square upon
mg
mg.
mg x square.
Mgx, yes.
So mgx is equal to kq square.
Upon.
Wait. So this is there's a tan theta here, right? I'm sorry. Where's the rubber here? So there's a
I guess we wanted theta, so we can do tan
just a
inverse kq square
No,
upon
no, no, no
mgx.
need, no need, no need, no need to do any of that, right? So you have tan theta here, and you know what tan theta is approximately from this triangle. It's x over 2 over L, correct? Or x over 2L.
Yeah.
So let's just put that value here. So you have x over 2L is equal to kq square over mgx. Take the x
So,
upstairs,
the
you get x square is equal to
mgx square is equal to kq square 2l
over mg.
upon mg.
So
Yes, sir.
x is essentially the square root of this whole bloody thing. Does this make sense?
So, but this won't give the answer because options are given as q square L upon 2 pi E naught mg raised to power 1 by 3. So it's showing cube root in each of options. And it's not showing 2L, it's showing L square and L. So basically, the only variation we have to do in our answer is related to L square L Q square and raised to power 1 by 3, which is cube root, as per the options which are given.
Oh, what am I doing? What am I doing? There is an x square here. There is an x square here. यहाँ पे मैंने x क्यों लिखा है? ये x square है, right?
Hmm.
This is an x square. This is an x square here. This will become an x
So
cube.
that will be raised to 1 by 3, yes, sir.
Yes, this will be a cube root of this. Sorry.
So this would be k is equal to 4 pi E naught. So
Yes,
1 by 4 by E.
k is just 1 by 4 pi epsilon naught. So your full answer, let me just remove some of this.
Q square, sir, but still we won't get 2L. 2L is not given in any of the answers.
I don't know. Well, things might change if you might have taken this as 2x, right? In the question rather than x. So that is why things might have changed.
Then we'll get sir 8x over there, because if we take 2x, then x cube will be equal to 8x cube.
No, not x goes to x over 3. Sorry, x goes to x over 2. Yes, yes. 8 times all of this. So, yes.
So that wouldn't make sense, because that wouldn't give us the answer, I guess. We are making some mistake with 2L, I guess, in the previous thing. Like, I'll tell the options which are given. Options are k q square L upon mg raised to power 1 by 3, k q L square upon mg raised to power 1 by 3, q square L square k upon mg raised to power 1 by 3, and k q square L mg raised to power 1 by 3. So what we have to play with is just the L. We have got the rest of the answer. So if we substitute q1, then we have three options left: L square, L, and yeah.
This L is going to be just.
Okay, got it, sir. What they have done is that they have okay. So for the question answers, they have done is that they have taken the value of k as 1 by 4 pi epsilon, and they have what do you say? Cut the 2 with the 4 of 2 pi. So we'll get k q square L upon 2 mg.
Yes, 2 mg. But pi भी होगा ना,
Yes.
2 pi epsilon naught. हाँ, ठीक है.
हाँ जी सर, तो 4 पाई और ऊपर वाला 2L कट हो जाएगा. Okay.
Yeah, that makes sense. Makes sense. But you understood how essentially all of this goes, right?
Yes, sir. So I got the answer. Yes.
Yeah. So it's essentially just balancing the force. That is all you need to do.
Ji, sir.
Okay, lovely.
And
So anything else?
well, yes, sir. I did a lot.
Go ahead. Go ahead. Go ahead. No, that's awesome. That's awesome. More the problems, the better.
So there is this question. Yeah, there is this question number 3 in the same assignment. I'll just read out the question.
Okay.
Yes, sir. So the question, so the figure is quite the same. The theta is given at 60 degree. There are two masses with same charge q.
So
Q
this
is
is
equal
60 degrees.
So I'll just read the question. Two small spherical balls, each carrying a charge q is equal to 10 microcoulomb, are suspended by two insulating threads of equal length 1 meter each. So we have been given the length 1 meter and charge as 10 microcoulombs, and two spherical balls at a point fixed in a ceiling. It is found that the equilibrium threads are separated by an angle of 60 degrees. So theta is given as 60 degrees.
Oh, this full thing is 60 degrees. Okay.
1 minute, sir.
Okay.
Yes, sir. Yes, sir. This is 60 degrees, and what they have given is what is the tension in the threads. So what I did was that I first took the value of k equal to 1 by 4 pi E naught is equal to 9 into 10 raised to power 9 Newton meters per Coulomb square.
Yes, yes.
And as the two and afterwards, like I didn't know how to proceed. So like I proceeded in another way. I put it equal to t. One k q square upon r square is equal to t. I did it that way. But in the answer solution, they give it
KQ
as k.
square over R square over X square will be equal to not T, right? It will be equal to T cos theta, which where
T
theta is
cos. That was the only doubt which I had because t it was given t into 1/2. Now I knew that t 1/2 would have half t would have come from sine 30 degree or because there were two masses. So this
okay.
was the doubt, like which one of it was prominent.
So
Was
essentially,
it
what you have is this, right? You have the Coulomb force here, and what you have is T cos theta here and T sine cos 30 degrees and T sine 30 degrees. So
yes, sir.
it's exactly the same process that we are doing. We have T cos 30 to be equal to mg and T sine 30 to be equal to kq square over x squared. Now, in the previous case, what did we do? Well, we found x as a function of other things, right? Now, we
Yes,
can just substitute that value back and calculate t here, right? From only this
G-
equation.
yes, sir. So I just used the second equation
Yes.
and I got the answer from that. Okay. T was coming 1.8 Newton.
9 to 10 is power 9. You have q square. So you have 10 microcoulombs. So 100 into 10 is power minus 12 divided by x squared. So
So why
what
would it be 100? It won't be 10 into 10 is to power minus 12.
100, right? So you
Okay,
have
okay. It's
10 into
square.
10.
Okay, I got it. So yes, sir.
Yes, yes, yes. So, okay. Is there an easier way to do this? Yes, there is an easier way of doing this. Why do I want to even substitute the whole thing? When you're given theta, right? You already know that in this triangle here, this triangle here, the L is given to you to be 1 meter, and this whole thing is x. So this is x over 2. Uh, So what do you have? You have sine theta or sine 30 degrees should be equal to x over 2l, and l is 1. So x over 2, and sine 30 is what? 1 by 2, correct? X over
1 by
2.
2.
So x is also just equal to 1. That's lovely. So let's just find out what t is. So you have
Sir, X
9.
was given. Sir, X was to already given 1 meter.
X was given to be 1 meter. L was given to be 1 meter.
Oh, okay, sir. Yeah.
But as it turns out, X will also be 1 meter. So we just got
इसे
lucky.
सही होगा सर फिर मेरा.
But that's just lucky. If the theta was different, the X will would have been different.
Yes, sir. So
So
what we have to do is we have to take sine 30 if the angle is given as 30 degree.
yes.
Then we'll get the
So you
that
have
thing.
1.8 newtons essentially. What you will get.
Yes, sir.
Make sense?
Yes, sir. And then, sir, there was the second assignment. I
Hmm.
had a doubt in question number 4. A
Hmm.
copper sphere of mass 2 gram
Hmm.
uh, contains about 2 into 10 raised to power 22 atoms.
Hmm.
The charge on the nucleus of each atom is 29 electrons.
The charge on each nucleus is 29 electrons
29 electronic charge, 29 E
on each atom.
on each atom. Yes, sir.
Wow. Okay,
The
wait.
mass,
So
the
total
mass of
charge is
so
just number into what is the number that you said?
uh, so the mass of the copper sphere is 2 grams and it contains about 2 into 10 raised to power
Yeah.
22
How many
atoms.
charges per wo? How many charges per wo? Per atom?
So
29 you said.
29 E electronic charge. Yes,
Okay.
sir.
So total
The
charge is
mass,
this. Uh,
and so it's given the mass of electron is 9.11 into 10 raised to power minus 21 kg.
minus
How,
31 kilograms.
yes, sir. How much mass will the sphere lose or gain, it is if it is given a charge of plus 2 microcoulomb.
If you add 2 microcoulombs to this, how much mass does it give? Oh, okay. So that's okay. That can be an interesting question, but I don't think the question is what I think it is. But
So micro,
okay, uh-huh. Yeah.
so
Okay.
microcoulomb भी लिया ना मैंने गलत तो नहीं बोल दिया क्या?
So charge
जी
is
sir.
given to be 2 microcoulombs. So you can just calculate the number of electrons from here, right? Number of electrons is just 2 microcoulombs divided by the charge of one electron, right? E.
Uh,
So 2 into 10 is power minus 6 over what is E 1.67 into 10 is power minus 19, right? So इसका भी unit coulomb, नीचे का भी unit coulomb cancel out हो जाएगा. So this will just be a number. So that means that we are doing everything fine. It's always good to check your units. It's always a good habit. So from here you can just find the number of वो 10 power minus 6. ये कितना बचेगा minus 13, right? 13, yes. So you have 2 over 1.67. 2 over 1.67, let's just say it will be around 1.5, right? 1.6, sorry, 1.4. Let's just call it 1.4.
1.4 into 10 raised to power 13.
Into 10 to the power 13, you will get number of electrons. Now you have the
Number of,
mass of the electron, of each electron. Just multiply
so we
these
have
two.
to multiply it by the mass.
Yes, so the total mass, m total, is just number of electrons multiplied by the mass of the mass of one electron, right?
Yes sir.
So that's just 9.11 into 10 to the power minus 31 into 1.4 into 10 to the power 13.
13.
And from here you get whatever you get. Hmm,
Why has he given the charge of one electron as 29 electrons? Where will we use that one?
I don't know. I honestly don't know. I think it's just a random thing that they've put in there.
It's I'll just check the solution. उसमें शायद दिया होता उन्होंने use किया था इसे.
How?
Uh, okay, wait a second. Yeah. To give positive charge to the copper sphere, a certain number of free electrons must be removed. The total number of electrons is 29 into 2 into 10 to the power 22.
Okay.
Okay, so इलेक्ट्रॉनिक चार्ज तो 29 है तो उसको नंबर ऑफ एटम से मल्टीप्लाई भी तो करेंगे.
Oh. So that will give you the total charge, right? That is what I
That
mean.
will give us the total number of electrons. So 5.8 into 10 raised to the power 23.
Wait. So 29 is the number of. Oh, okay.
So I don't know why he has given this because
This is a
I
very
can't
confusing
see
question.
I can't see it being used anywhere further in the calculation. So
Let it be. It's a
he has
weird
just
question.
specified that the total number of electrons is 29 to 2 into 10 raised to the power 22.
Hmm. What question is this? Can you just tell me? Assignment and question number?
So this is JEE B2 batch physics class 12 electric charge and feed electric charge assignment. सर इसमें सिर्फ MCQ है चार questions है MCQ के and this is the fourth question.
ठीक है. Okay, I'll
Like,
go through your data and I'll
it
figure
is
it out.
it is the latest assignment जो भी
Okay.
recently आई थी.
Okay, lovely. No problem. No problem.
And
Okay, let's get started with today's class. Can we?
uh, सर एक और डाउट है बस.
Okay. Go ahead.
फर्स्ट असाइनमेंट का फिफ्थ क्वेश्चन. यस सर 1 minute. Yes, sir. So the question is two identical balls have like charges and placed at a certain distance apart repel each other with a certain force.
Hmm.
They are brought in contact contact and then moved apart to a distance equal to half their initial separation.
Okay.
The force of repulsion between them increases 4.5 times in comparison with the initial value.
Okay.
The ratio of the initial charges of the balls is.
I mean, so initial condition पे तुम total force निकालो F
मैंने कर दिया इनिशियल पे तो सर नॉर्मल फोर्स आ गई के Q1 प्लस Q2 होल स्क्वायर अपॉन R स्क्वायर.
yes
सॉरी ये
X2.
तो सर F नॉट है जो सर
This is
मैंने क्या
F1.
किया.
What is F2?
सर
F2
वन
is
मिनट. So what I did was that I took the initial one as F is equal to K Q square upon R square.
uh,
Second, I took the final situation in which I took both the charges as Q1 plus Q2 by 2 and Q1 plus Q2 by 2 and distance as R by 2 because it tells that distance has been reduced to half.
but both
So
are Q1 and Q2 are is the same, right? uh, it says that they are like charges.
so they're like charges. I guess the question meant that they both are positively charged or negatively charged. They are like charges, but they didn't tell the magnitude to be equal. Because
Ah,
if the magnitudes were equal, the
makes no
force would
sense.
have been directed. So, but
Yeah.
then the force will be in direct proportional of 1:4, and it's telling that the force are in proportional of 1:4.5.
Yeah, makes sense,
So
makes
there
sense, makes
to
sense,
be some
makes sense.
separation.
Yes, yes, it makes sense, makes sense. Q1,
So,
Q2.
what I did was that I took the new force, the final force, as K Q1 plus Q2 upon 2 whole square upon R by 2 whole square. That gave
Hmm.
me, that in short gave me K Q1 plus Q2 square upon R square.
Hmm.
Now, as per question, I took the ratio as F naught is equal to 4.5 F,
Hmm.
and then I replaced the value of F naught and F in the equation,
Hmm.
and then I got 4.5 Q1 Q2 is equal to Q1 plus Q2 whole square. Now
Hmm.
I don't know how to proceed after this because I couldn't get the ratio of Q1 upon
That's
Q2.
that's just a simple. Wait, if 4.5 is equal to, can you say that
Uh,
again?
which one, sir?
Q1 plus Q2 whole square, right?
1 plus F, sir.
Wait,
1
wait, wait.
plus
All of this removed. So this here equation here. Here. This is what you have, right?
yeah, yeah, this.
Okay. So how do you simplify something like this?
So that was the question.
Yeah. So I know that was the question. Uh, I'm thinking about it. Let's just open it, no?
So he even tried this. The 2 will go there, and then it will get minus 2.5 Q1 Q2.
Dividing by Q1, Q2 on both sides, what do you get? Q1 over Q2 plus Q2 over Q1 minus 2.5, right?
Q1 Q2 on both sides. Yes, sir.
Yes. Okay. So now look at this trick. So look at this trick. So let's say Q1 over Q2 is some x, okay? So what does this mean to the equation? It means that this is x plus 1 over x
Minus
minus
2.5.
2.5, correct? This
Yes,
implies
sir.
0 is equal to x square minus 2.5x
Minus
plus 1.
2.5
What is this?
plus.
What is this? This is a
So,
quadratic equation.
yes, sir.
So this implies x is what? Minus b, so 2.5 plus minus square root of b square, so 2.5 square, which is 6.25, minus 4 into a to c, 1 into 1, divided by twice of a is just 1. So this
2.
just becomes 2.5 plus minus square root of 2.25, which is just 1.5, as we know. So this is 2.5 plus minus 1.5 over 2.
4
So,
comma 1 by 2.
so
So 2
now
by 1 by
you can have two answers. Just give me a second.
2 and 1 by 2.
Let me just remove these. So your x can be equal to
2 and 1 by 2. 2 and 1 by 2.
2 and 1 by 2. So essentially,
Yes.
what does this mean? This means that your q1 over q2 can be equal to 2, or the ratio can be opposite. So it's essentially the situation is symmetric. That is what these two,
Yes.
yes, that is what
Both
they are
the answers will
representing.
be correct.
Yes, and so they are symmetrical essentially. That is what it's representing. Does
Okay,
this
so,
make
so what
sense?
we did was that we wanted a constant at the C place, so we just divided the variables of the C
On
part
both sides?
on
Yeah.
both sides so that C gets cancelled out, and then we took both the variables equal to X so that we get a quadratic equation.
Yes.
Perfect. Okay, sir.
Nice. Okay. Let's start.
Yes, let's start.
Okay. Okay, so let's start today's class. We're going to talk about electric dipoles. We should have revised what we've done in the previous classes first, but it's fine. It's fine. We'll just start with the electric dipoles. So, what is an electric dipole? It's a very, very simple concept. Well, it's essentially the next step one will think about once they've already thought about point charges. So, point charge, as we remember, can be of two types: the plus charge or the minus charge. Most simplest configuration that you can think of is essentially take a plus charge, take a minus charge, put it at some distance. Let's call this distance 2a, because let's from the center it's a. So let's call this total distance some 2a, and let the left hand one be the negative charge and the right hand one be the positive charge. Why are we using this convention? Because if we remember the number line, the negative side thing is always on the left hand side and the positive things are on the right hand side. So it's a good thing to always keep in mind कि हमारा convention हम क्यों use कर रहे हैं, जो भी use कर रहे हैं. Then okay, so you have these. So this is what a electric dipole is. It's the simplest configuration of a plus charge and a minus charge. Just bring them together at some distance and then see what the different kinds of things this system brings out. So what meaning? What kind of electric field does
So,
this kind of a system emit? That is essentially the problem that we are going to talk about. But before
so we
that, yes.
of the electric field, like it will be a positive electric field or a negative electric field.
We don't know. We'll figure out very soon.
Okay.
Okay. So one more quantity that we define with every electric dipole is you can think of it like a charge for the dipole, like an effective charge of the dipole. We call it the dipole moment. This dipole moment is given by the variable p, by the alphabet p, and it's a vector quantity. And by convention, its direction is from the negative side to the positive side. So, meaning that if we come back to our analogy of the number line, where negative things are on the left hand side and positive things are on the right hand side, this vector will always be in the direction right hand side. Does that make sense?
Yes, sir.
Lovely. So this is all convention, and this is all essentially how we're defining. Now, this dipole moment, when we're defining, we're essentially just defining it as the charge that these individual things have, the minus q charge and q charge, multiplied by the distance between them. Notice that this quantity will be a constant. So it will be a constant vector. And in what direction? Let's call this direction p hat. Let's call this direction p hat. Okay. So the charge, whatever charge these individual charges have, q multiplied by the distance between them gives you the dipole moment. This is a very, very important quantity. as you'll see in the future, because most of the things that you see in nature after being single charges, because since this is the most simplest configuration one can think of, it stands to reason this will be the most abundant also, one of the most abundant also, right? Simplest things happen more often. It's just a law of nature. So where all do we see this? Well, the simplest example one can think of is NaCl, sodium chloride. So sodium chloride, if you remember, sodium has a plus charge and the chlorine has a negative charge. So it's essentially like the sodium atom, which is just sitting here without an electron, so with a minus with a plus E charge, and a chlorine atom sitting here with an extra electron with a minus E charge, with a certain distance between them. The distance between them is what is called the bond length, right? So essentially, bond length is just equal to 2a. So studying these kinds of system, as you can see, is one of the most basic problems, because they're talking about ionic compounds, and most compounds that we know are ionic compounds. So dipole nature will be seen in these kind of things. Now, when I talk about the nature of a dipole or the nature of a monopole, for example, a charge, what do I essentially mean? What I mean by the nature uh, is essentially how the electric field behaves, the electric field behavior. And when say the behavior of the electric field, what I essentially mean is that the electric field we know is going to be a function of R, correct? Now, what dependence there is to the power n, whatever this n is essentially dictates the behavior of the system. So for a point charge, we already know that the electric field is just r to the power minus 2, correct? Is dependent on r to the power minus 2. So n is just equal to minus 2. So it has a particular behavior. The kind of behavior that we see for an electric field is because of the fact that it is a 1 by r square force, or 1 by r square field. It's because of this fact. A 1 by r cube is a very, very different kind of a field. And we'll see where that 1 by r cube comes right now. So let's imagine a situation where you have a
Uh,
dipole. Yes, go ahead, go ahead.
so I understood that electric field is a function of r, and the raised to power r raised to power something is n will be constant.
Yes,
So
r to the power n will not be a constant. No,
like
no,
it
no, no.
can be, but it can tell us about the field basically, like
It
positive
will
or
tell you
negative.
about the field. Yes, that is how fields are characterized.
Yes, sir. But
But
what exactly is r?
r is just the distance from this from wherever the charge is kept.
So
So
the
charge
bond
is
length.
no, no, no. If you have one charge, so it's kept at the center. So how far away are you? So for example, you're here, so the distance will be r. If there is a dipole and you're here, so it will be the effective distance from the center of the dipole. This will be the r. So it's essentially from the center of the system how far away you are. Make sense?
Oh, yes, sir.
So r essentially tells you how far away
And
r
so
is being.
if we say that r is the distance from the center of the system,
Yes.
and we are saying r raised to power n, so
Uh,
what exactly do we get over here? Like
so
r
it's
raised to power n is distance raised to power n.
so essentially we have a function which is proportional to 1 by r to the power, let's say 1 by r to the power n, okay, rather than r to the power n. So if you plot these functions, if you have e as a function of r, let's try to plot some functions, okay? Let's see what these functions look like. Let's try to draw the first simplest function, which is just r, linear. Lovely. What about r squared, where r squared is quadratic? So that's how it looks like. What about r cubed? Well, r cubed, do you know how r cubed looks like?
Uh, no, sir.
So the left hand one comes down and the right hand one goes up. So it's essentially like this. So notice what is happening. First you have x which is a line, then you have x square which is a curve or a parabola, then you have x cube which is like this. So it has three endpoints. So it's turning twice essentially. The next one will obviously turn thrice. The next one will obviously turn once again. So that's essentially how the positive things look like. What about the negative things? What about x to the power minus 1? Well, that looks slightly different. Let's try to draw that. So 1 by r. So if you want to plot 1 by r with respect to r, well, as r tends to 0, 1 by r tends to infinity, right? So it will start from infinity and it will come down and will keep on coming down. This is how 1 by r looks like, right? What about 1 by r square? Well, 1 by r square will come down even faster. It will come down even faster and it will go to 0 even faster. So it will cut somewhere and it will go to 0 even faster. Xr cubed will come down even faster and will cut somewhere and it will go to 0 even faster. So it just keeps on becoming faster and faster. It just keeps on converging to this point. So if we take n tending to infinity, what does this becomes? It just
Zero
becomes a straight line here and a straight line here. That's all it is.
along the axis.
Yes, along the axis. A straight line down and a straight line this. You'll see this somewhere else also as a delta function. You can run your imagination as wild as you want. Um, when you'll see it, you'll know what I'm talking about. Okay, lovely. So we were talking about the dipole. Yes. So let's try to calculate the electric field along the dipole. So let's say this is the dipole and this is the direction along the dipole, and we are at some point P here. The center of the dipole, let's call it O. We already know this distance is A and this distance is A. So the coordinate of this would be minus A comma 0 and the coordinate of this point will be A comma 0, correct?
Yes, sir.
So this point P is at some P comma 0, right? Because everything is along the x-axis right now. Now, what is the electric field because of the first charge? So let's say this, so we know that this is the negative charge and this is the positive charge, always following conventions. Um, what is the electric field because of the positive charge? So we'll call this 1 and we'll call this 2. Tell me.
Uh, the electric field cause of the first charge.
Yes, at point P here.
Sir, it will be E as a function of A raised to power 1.
As in, what is the electric field? See, electric field is just the
Sir,
force divided by the charge, right? By the unit charge. So electric field, so what is the force that will act because of this charge from here to here? Well, it will just be your K times the charge, which is plus Q over R squared, right? The distance between here to here. But what is the distance between here to here? Well, we don't really know. Well, but we know what the distance from here to here is. It's P. And we know the distance from here to here, this is A. So the distance from here to here, well, this is just P minus A, correct?
yes, sir.
So this is just P minus A whole squared, correct?
Yes, sir.
So in what direction?
Sir, in positive direction.
In the I cap direction. Let's call this direction I cap because it's along the x-axis, right? The second, what about the second charge? Well, we know that the charge is negative, so it's minus kq over.
It will be minus kq over p plus a whole square minus minus I charge minus I charge.
But there's a
So
minus
wouldn't
sign
it?
already here, right?
Oh, okay. Yes.
You don't need to put in two negative signs. So then what you are essentially doing is
Yes.
you're negativing a negative, which essentially gives you the same thing. Okay, so what will be the total field? Well, it will just be E1 plus E2.
So,
So says the superposition principle, correct?
yes, sir.
So let's just add them. What do you have? You have KQ over P minus A whole squared minus KQ over P plus A whole squared. In what direction? In the direction I cap. Lovely. Okay, now let's go ahead and simplify this. So let's take the KQ out first of all. So you have 1 by over P minus A whole squared minus 1 over P plus A whole squared. Like that. Now, any suggestions on how one should proceed here?
Uh,
Well, the
so let's
simplest thing would be just to multiply them
yes.
together, right?
So let's open the brackets and multiply or direct multiply.
Direct multiply. Why do you want? Multiply not inside, as in multiply these two together. So take common essentially. P plus A whole square, correct? So what do you have? You have P plus A whole square minus P minus A whole square. Lovely. Well, looking at this, your eyes should shine. Why? Because whenever one looks at an expression like this, the first thing to notice is the squares and the negative signs, correct? And we know
Yes.
a very, very nice property, which is that a square minus b square is equal to a plus b
Yes.
into a minus
A
b,
plus
right?
B A minus B. Yes, sir.
Lovely. So the bottom thing already we know is just going to be p square minus a square. But not only that,
Yes.
even the top thing is just a square minus b square hidden, right? So what this will this be equal to? So you have kq over a square minus b square. So you have p plus a plus p minus a multiplied by
Minus A.
p plus a
B
minus
plus A
p plus
minus B plus A.
lovely divided by p square minus a square whole square.
So
Makes sense?
2P into 2A. So that will be 4AP.
Yes, perfect. So this will be 4ap over p square minus a square whole square. Now, notice that the p we are using here is just the distance from the center, right? So this p is essentially just my r, right?
1 minute, sir.
हाँ हाँ आराम से take your time.
So P square minus A square.
Whole square. ये कैसा है?
After opening this.
See, this is a minus b into a plus b, right? This is the right hand side of this. So this is just p square minus a
So,
square.
so, so wouldn't it be P square plus A square whole 2, whole multiplied by 2?
Whole multiplied by 2 नहीं whole का power 2.
Yeah, whole का power 2. Yes, sir.
हाँ so whole का power 2 है तो यहाँ पे
So वो प्लस नहीं होगा, माइनस क्यों होगा?
because there's a minus sign here.
Uh, wait, एक मिनट. ये हमने
Let's
P
let's
minus A
open this.
whole square.
Let's open this. Why are we confusing ourselves? Why are we confusing ourselves? Wait, p minus a whole
So
square.
P square.
कभी भी confusion हो, do it normal. So what is this? This is p minus a into p plus a whole squared, correct? So let's
Yeah.
open this.
So,
This is p square minus ap plus ap minus a squared का whole squared, correct? The AP and AP cancel out, and this just gives p square minus a square whole square. Make sense?
Yes, sir.
So
Sir,
why
but if
my
we put them individually, like if I do p minus q whole square, that would give us p square plus, oh, that would be,
no,
oh,
no, no.
ठीक है,
That will also give you the same thing. That will also give you exactly the same thing. But आपका
yes,
calculation बहुत लंबा हो जाएगा और कुछ नहीं होगा.
got it, sir. Yes, sir.
Yes. Okay. So now this kind of a solution is super interesting. First of all, whenever you achieve some any solutions like this, actually before that, realize that my p is just r, right? It's just the distance from the center.
Yes, sir.
So my actual e total, if I want to write it down here, that I'm getting at the end in terms of r as a function of r rather than being as a function of p, it's just k q 4a times r over r square minus a square whole squared. In what direction? In the direction I cap. Make sense?
Yes,
Now, whenever you achieve an answer like this, where you have something as a function of distance, it's always a good idea to see how things behave at large distances. At when r tends, when r becomes actually greater than a. In this regime, I think are you, Yuvraj, are you there? I think your internet went off.
yes, sir.
You're here. Okay, lovely. Um, yes. So first thing you need to you okay. So whenever you achieve a solution where you have some kind of a field or some kind of a force as a function of r or a function of distance, always see what is happening at large distances, because that's essentially the behavior that you will see. Because since we already know the dipoles that we are talking about here are going to be molecules, are going to be things like NaCl, and so the distance a between them, and we're seeing them, we are macroscopic creatures, and we're the ones who are measuring them. So our r is obviously going to be way greater than a. So let's see what is happening in this regime. Well, if r is greater than equal to a, then r square is super greater than a square, right? Correct?
Yes, sir.
Lovely. So that means in the denominator, you can just ignore the a square. So I'm essentially just writing this as 4ar over r square ka whole squared I cap. Make sense?
Ji, sir.
So this is essentially approximately equal to. So there's an r upstairs and there are four r's downstairs. So one of the r will go away, and what will remain is just kq 4a over r cubed I cap. Now, isn't look at this. Isn't this interesting? What the answer you received here?
Sir,
What is the interesting bit here in this answer?
mm, sir, that r square is very, very greater than a square, and then we get r cube.
Yes. So essentially, what we're getting is an r cubed. So what
Yes,
I'm
sir.
saying, so I'm clearing everything. You've written everything down, right?
1 minute, sir.
Okay. Just write everything down. I'll remove things.
Sir,
Yes.
okay, nothing, sir. 1 minute. So why did we cut the T from there?
You cut the
A A R. So the AP 4AP. So we just took 4A.
यहाँ पे this thing.
Uh,
No, that is not p. The p we removed, right? P we removed.
yes.
P is r. P is just r.
That was I was wondering, sir. So
Yeah,
this
P
would be
was R. So, yes. So the R essentially cancels out from the denominator, right? One of the R.
yes, that's why we got
Yes,
4Q
the R cube. Yes,
RQ.
lovely. Okay, I'm clearing this.
Ji sir.
Lovely. So our E total that we got for an electric dipole for large distances, mm, mind you, it's just K times Q times 4A divided by um, what was divided by R cube. Yes. Now this is a very different behavior. R cap. Well, let's say because it's in some distance. Let's call it R cap. This behavior is very different from the behavior of a monocharge, of just a charge, because just a charge at large distances we already know behaves as 1 by r square, and this is a pattern that we'll see. This is a pattern if you go ahead and increase the complexity. So this is what is essentially essential to notice here. If you have one charge, your electric field will depend on 1 by r square. If you have two charges, so a dipole, your electric field will go as 1 by r cubed. When you have three charges or a tripole, as one call them, you will have E proportional to 1 by R4. You have a quadrupole. Your electric field will be dependent on 1 by R5 and so on and so forth. And there is a theorem. There is a theorem in electrostatics which essentially tells us that all electric fields can be written as a sum of these powers. So essentially, you will write them as some constant times these powers, r to the power I. Some constant ci multiplied by r to the power I and sum over I. So essentially meaning that for any general problem, if you want to calculate the electric field, essentially what is happening is that every system that you have can be broken down into its monopole, dipole, tripole, quadrupole components. Does that make sense?
Yes, sir.
So at the end of the day, all charges are essentially made of these monopoles, dipoles, tripoles, quadrupoles, and this is how we essentially prove that.
So, sir, this basic electric charge that we have found,
Hmm.
electric field, sorry, just
Hmm.
tells us if the field is a straight line, a dot, a triangle, or a square by
And
the relation of the field with respect to the distance squared, distance minus 2, distance minus 3, minus 2.
yes, absolutely. So, I mean, there might be a direct question where you're given like a quadrupole and they just ask you, okay, which will be at the electric field. So, just by seeing the quadrupole, you should be able to know that it's going to be r to the power 5.
Oh, r to the minus 5, right?
R to the minus 5, sorry, yes. 1 by r to the power 5, I meant.
Answer this though was r raised to power minus 2, minus 3, minus 4, minus 2. But
Yes.
what if we took r to raised to power 2, 3, 4, 5, the positive ones? What
Lovely,
will we get?
lovely question. Turns out, um, you obviously you can create fields which are linear. You can create fields which are non-linear, also x square kind of field. But those systems are very very complicated. So essentially, what you need to do is make these laser lenses essentially. Usse you can control each atoms and you can bring up call configurations in which this will happen, proportional to r. So actually we will see proportional to r, so we will see proportional a sheet will have electric field which will, yeah, we'll see these examples. That's a good question. We'll see those examples also. Lovely. It's a lovely question. Okay, so we found out what the electric field was for a dipole along its axis, right? Now, what
Yes.
about the other direction? What about perpendicular to the axis? What about not being along? What about being perpendicular to the axis? So you have here, and you're somewhere up here, let's say. You're up here, let's say, and you have these two charges again, the negative charge on the left and the positive charge on the right with some charge Q and distance A away from the center as always, and the center is called O. Lovely. So let's start again. What's the electric field because of the first charge? Let's call this charge 1, let's call this charge 2. So you will have a triangle that forms, correct? This distance, let's call this distance some y, right? So this is A, this is Y. What is the electric field going to be then?
So electric field will be
At this
uh,
point P, because of this one charge. It will just be KQ over the distance squared, right? And the distance squared is just y
square.
squared plus a square, correct?
So a y square plus. Oh, okay. It is dropping from a length of a. The
Yeah.
mass.
See, no, no, it's not dropping. It's just kept there. No, no, there's no mass here. There is no mass here. Wait. Let me clear everything. Let's start all over again. We're talking about the electric field due to a dipole on its perpendicular to its axis. Sorry, not on its axis, perpendicular to its. So you have a dipole with charge minus q and charge q here at a distance 2a away from each other, correct? The center point, let's call it O. Now what we're seeing is what is happening in the direction perpendicular. So we're seeing what is happening in this particular direction, right? So let's say we're here at this point P. At this point P, what is the electric field because of these two charges? Well, it will just be the sum of the two electric fields, right? So what's the first electric field going to be? Well, it's just going to be K times Q divided by the distance between this P and Q, right? So essentially this distance L, so L squared, but L, this distance is some Y, as I said, and this distance is some A. We notice that it's a right angle triangle. We can use Pythagoras theorem. So this just tells us that this is just y square over a square. Make sense? Similarly, because of this, but in what direction? In what direction?
So which one? The it would be in direction of L.
Huh?
So it would be in direction of L force.
Yes, because it's a positive, so will it be inwards or outwards?
So outward.
Lovely. And what about the minus one?
So inwards.
Lovely. Okay. So your net field essentially be in this direction. Okay. So this is your E1. And what about E2? Well, what is E2 going to be? Well, it's going to be, sorry, this is in the direction E1 hat. Let's call this direction E1 hat, and let's call this direction E2 hat. Sorry. Okay, KQ over with the negative sign, obviously, meaning that it's coming inside. Again, y square plus a squared, but in a different direction, in the direction E2 hat. Make sense?
So I had a question.
Yes, go ahead.
So minus Q and Q, these are 2 points, and this is a dipole, right?
Mm.
and it is perpendicular to its axis, and we have taken a point P on its axis, right?
Yes, yes.
And from this point P, we have taken from Q, from the charge Q, we
Hmm.
have taken P as in the direction of E1, and
Hmm.
from the point minus Q, we have taken it as E2, right?
Hmm.
Okay, थोड़ी confusion थी clear करके बस.
Okay, okay, okay. This is E1 and this is E2. Absolutely correct.
Yes.
Okay, now clear thing to notice here, the y components of both. So the E1, let's call this angle some theta. This angle will also be theta. So E1 cos theta and E2 cos theta will essentially cancel each other out. So there won't be anything along the y-axis. Whatever will happen will be along the x-axis. So we'll have to take the x components of both of them. So the E total vector will essentially be the x component of E1 or E1 sine theta plus E2 sine theta. In what direction? In the direction I cap. Make sense?
I yes. Sir.
Lovely. So let's just substitute the values. Quick question, what will sine theta be? So if this is theta, this is also theta. What will sine theta be?
The sine theta will be.
It's perpendicular.
So we haven't given any angle, right? We just know that the angle is 90 degrees.
Angle is 90 degrees.
Uh,
Only
over
V is
here,
90
yes, sir.
degrees.
Over here. Yes, sir. That is at 90 degrees. We haven't been given any of the angle, right?
Let's take it to be some theta now. And we know the sides. We know the sides that's useful.
Yeah, over here. Yes, sir.
Yeah, well, lovely. Okay, let's substitute the values. What you get KQ, 1 over y square plus a squared into sin theta, yes. Uh, into sin theta. So, okay, so these two are essentially the same. So they will add up. Mm, No, let's actually just do it nicely now. So this is the sine theta plus 1 over y square plus a square sine theta. So this will just be twice of this whole thing. Let me just move these to put some space.
Excuse me, sir.
Yes, go ahead.
Sir, the value of E2 which we got was in negative, right?
Yes.
It was negative, and what we are doing is E net is equal to E1 sine theta plus E2 sine theta. So
Yes.
wouldn't the value of E2 sine theta will also be negative? So it would be
No.
1 over y square plus a
No.
square sine theta minus u.
No. No, no, no. There is a negative sign there, absolutely. But what does that negative sign represent? It represents the fact that it's
So
coming inside.
direction.
It's representing the fact
Yes,
that
sir.
it's coming inside. It's not going
So we are
outside, it's
just
coming
taking
inside.
we are just taking the magnitudes over here,
Yes,
not the
yes,
direction,
yes,
right?
yes, yes. We're just taking the magnitude.
Okay, sir.
Because
So we can
negatives,
even place the negative sign. We can even place the negative sign next to the E hat.
even, yes, then both will be negative, so there will be an overall negative sign. But it doesn't matter, it's just convention. It's just based on your convention.
Okay.
Lovely. Okay, so what you have is 2kq over y square plus a squared times sine theta. Now, what is sine theta? We already calculated it was a over L. So what you have 2kq times a over L. L is just y square plus a square. L is just y square plus a square to the power one third, correct? 1 2, sorry, power half. So this whole thing just becomes kq times 2a over y square plus a square to the power 3 over 2. And in what direction? In the direction I cap. Make
So
sense?
how did we get 2A? Okay, 2 was placed over there. Okay, sir. Then this will be 3. Yes, sir. Makes sense.
Make sense? Now,
Yes.
compare it to the previous case. What were we getting?
So in the previous case,
Tell me
we were
what we're getting.
so E net is equal to KQ 4A upon RQ R cap
R plus R
Q.
square plus A square का whole cube, right?
So सीधा R wait,
No, three better. What were we getting? Yeah, this only we were getting, right?
सर मैंने तो R cube लिखा हुआ है because this was R square का whole.
But no, but R cube was at a distance very far away, right? So,
Yes, sir.
but R square minus A square था वहाँ पे. Oh, there was an R upstairs also. Okay, let's just talk about long distance then only. Small distance. करना भी क्या है. So this is just R cubed, as you rightly said, and my Y is essentially my R, right? Y, how far away you are, is essentially my R. So my E perpendicular is just KQ to A over R square plus A square to the power 3 over 2. Now, again, let's do the same thing where we have r greater than equal to a. So again, r square is again greater than equal to a squared. So we can ignore a squared in front of r squared. And hence you can write this thing down as kq into 2a over r to the power 3. So this is in the parallel direction and this is in the perpendicular direction. Now, notice what is happening. As soon as you're switching from the parallel direction to the perpendicular direction, your electric field is going down by half. Is it or is it not?
So could you just repeat the last line?
Yes. I'm saying that when you go from parallel to perpendicular, or from the first case to the second case, my electric field strength goes down by half.
Yes, sir.
And that is essentially the strange property of this electric dipole. One of the strange properties of this electric dipole.
So
Um,
this आ जाएगा ना?
if we have E perpendicular divided by E parallel for large distances, so I'll just write large R is equal to for large R. So that's why I've written it upar or niche, the equal to sign. It's just going to be 1 by 2. This is a slightly important thing to remember. Some many a times you can solve questions directly if you remember this fact that the perpendicular and parallel components of the electric field for an electric dipole are going to be of the ratio 1:2. Make
Yes, sir.
sense?
Can we move back to that?
Move back to the previous slide.
Yes, sir.
I can try. Yes,
Undo,
sir.
undo, undo.
Undo.
Then, sir.
Lovely. Now, one more thing to notice here. Uh, Notice in both of these things, you have a Q multiplied by 2A, right? And we've
Yes,
already defined something known as the moment, right? Which is essentially Q times 2A, correct?
yes, sir.
So the parallel thing can be written down very simply as K
2PQ,
2kp divided by
KP.
r cube, and the perpendicular one can be just written down as kp over r cubed.
सर Q कहाँ गया?
p की वैल्यू में q है.
अच्छा, ओ, okay.
and P
So
itself
still
is a
we are
vector. P itself is a vector, and इसका direction जो है वो I cap ही होगा. Yes, in this case, because it's from negative to positive always. So when you write this terms, these things in terms of the moment, this is how it essentially looks like. So I can give
so
you like,
this is
sorry,
so
go ahead.
this is used when we have to use it in terms of moment. Huh?
In terms of limit, no, a lot of times what will happen, as you'll see, so okay, I'll give you an example of, for this exact problem. Um, let's look at this problem here. So let's say you have three dipoles. The first dipole is such that you have the dipole moment in the upward direction. The second dipole is such that you have in this direction. Oh, sorry. Yes. Up here in this direction. So P2, and you have a third one, which is, let's say, up in this direction, P3, and you need to find out what the electric field is going to be at exactly the center. So these are perpendicular, and this is essentially parallel. So what is the electric field at the center? So let's say all the distance between these 3 points are equal, and they're A. So our total electric field will essentially just be the sum of the electric fields, correct? Correct?
Yes, sir.
The electric field because of 1, how much will it be?
Sir,
Since you are talking about along the axis, it's going to be twice. So just write
yes,
2, always write k, always write the p over is a cubed, plus the perpendicular versions for the 2. So you have k uh, p2 over a cube and minus k p2 over a cube. Yuvraj, are you there?
yes, sir.
Lovely. Does this make sense?
Uh, yes, sir.
Plus, so 2p1 plus p2 minus p3. Sorry, minus p3. Essentially, this is what the total total electric field would look like.
So this is when we have to add three electric fields.
Yes. So essentially, point being that a lot of times what will happen is you're just given the magnetic moment. And not only that, there are experimental reasons for why we use magnetic moment. A lot of times you'll see this in recurring in physics, where a lot of quantities won't really make sense why we're using them, and to only make sense of them, you'll actually have to go to experiments and see what quantities are they able to measure. And dipole moment turns out to be one of those quantities which are relatively easily measured, and it actually has been measured up to a very high accuracy. um, from the last estimates I've seen, the accuracy is like measuring the length of all of North America to the width of a human hair. So it's that accurately known what these moments are for natural substances. Uh, So yeah, okay. So I think we should just stop here, and we should continue with dipole moment day after.
Yes, sir.
Lovely. And if you have any other questions, you can
1 minute.
keep them.
Yes, sir. I
And
have two things.
yes, absolutely. We can actually just arrange like a doubt session once a week if you want that.
So that actually depends. This time I had assignments and also I was solving them and I had a test to solve. So that's why I have doubts.
Yeah, I mean that too obviously will be there. So we can like set up once, two every 2 weeks or 3 weeks, whenever you're comfortable. We can just sit and discuss your problems, whatever problems you have. Okay.
Perfect. Sir. When I'm just logging in to Learnivio.